Okay, I think time is up for the next talk. So the next talk, titled Semi-Definite Programming Strong Converse Bound for Quantum Channel Capacity. And the speaker will be Xin Wang from University of Technology, Sydney, where I'm from as well. Let's welcome the speakers.
Yeah, thanks, Michelle. Okay. Today I will talk something about quantum channel capacities. And this is a joint work with Wei Xie and Ren Yao. And both of us are from the QSI at UTS. So firstly, I would like to thank QIP Conference for providing wonderful tutorials every year. And last year, Aaron Harrow gave the tutorial about quantum Shannon theory and asked for non-trivial upper bounds for classical capacity. And John Waltries gave the tutorial about semi-definite programs. So after attending this tutorial, I just think about let's combine them. And I will study the capacity problems from the perspective of semi-definite program. So as you already, in the previous talks, you already know quantum channels, just CPTP maps, and there are several equivalent representations. One is the Stigner-Spring representation. The whole process is just isometry from Alice to Bob and the environment. And if you trace out the environment, you obtain the channel from Alice to Bob. And if you trace out Bob, you obtain the channel from Alice to the environment. And another useful representation is the Troy-Jamikowski representation. It is just applied identity map and the channel over the unnormalized maximally entangled state. This representation is actually very useful since it allows us to use positive semi-definite matrix with linear constraints to represent a quantum channel. And the capacity, so with quantum channels, we use to transmit information, classical, quantum, or private information. And the capacity is just the maximum rate for asymptotically error-free data transmission using the channel many times. So we first focus on the classical communication. The classical capacity is established by Holevo-Schumacher-Westmoreland theorem. It states that the classical capacity of a quantum channel is given by this regularization of the Holevo information here. And however, it is difficult to evaluate this quantity. Even for the one-shot Holevo information, Beige and Short shows that it is an NP-hard optimization problem. And also, the worst thing is that this quantity is not additive. It is proved by Hastings in 2009. And even for the qubit amplitude damping channel, the classical capacity is unknown. So this classical capacity actually characterizes the asymptotic capability of the channel to transmit classical information. And since we always have a finite resource and we are still in the early stage of quantum information processing, we have to consider some practical question. That is, given finite uses of the channel, how to efficiently evaluate or optimize the trade-off between the communication rate, that is, the amount of information we can transmit over the channel, and the error probability epsilon of the information processing. We also need to consider the assisted capacities. That is, Alice and Bob can use auxiliary free resources to assist the communication. The motivation of consider assisted capacities is that we can use it actually to increase the capacities, and sometimes it will simplify the problem. One such example is the entanglement assisted capacity. When assisted by entanglement, the classical capacity formula is very beautiful. It's just a single letter optimization problem and can be efficiently solved. This entanglement capacity is given by Bennett, Shaw, Smalling, and Saplia. So based on this background, in this talk, we will firstly focus on the non-asymptotic communication capability. That is, the first thing is given rate, what is the maximum success probability of transmitting information at this rate? And also, given an error tolerance, how much information can we transmit over this channel? And then we will use some kind of one-shot results to derive or explore the asymptotic capability of transmitting information. We will provide non-trivial upper bounds for classical and quantum capacities of general quantum channels, and also use it to study some specific basic channels. And both these results will be given by semi-definite program. And we note here this SDP is analytical tool in proof, and you can watch this book for more details. And this SDP can be efficiently solved by interior point algorithms, and you can implement it on your computer, combining the CVX software and the quantum toolbox QtLab. So let us start the one-shot information theory. The information, Shannon is the father of information theory, and in his famous paper in 1948, he said that the fundamental problem of communication is just reproducing at one point, either exactly or approximately a message selected at another point. That is, Alice and Bob use encoder and decoder and the channel N to communicate, and they hope they can transmit messages from one side to another side approximately. And we use the optimal success probability to measure this capability. That is, we maximize this average success probability over all the possible encoders and decoders. And we can transform this into some kind of quantum language, and this K is just the computation basis. And then with this optimal success probability, the classical capacity can be defined in this form. Maximize the rate R such that the communication has no error in the limit of the channel use. So now the key question is how to solve or estimate this optimal success probability. And this is the optimization problem, and we note that the main difficulty we made is the channel M. The final channel we obtain is composed by the encoder, the channel, and the decoder. So one smart idea is to think this encoder and decoder as a bipartite operation. And since we are doing communication, we hope this bipartite operation is with non-signaling constraint. That is, Alice and Bob cannot use this bipartite operation to communicate classical information. This is the so-called non-signaling code. It was first studied by Liang and Marshall for quantum communication, and Wanfors and Winter for zero-error communication. And it is also known as causal operations in physics. Also, the classical version was being used to study zero-error communication and classical communication by Cubitt et al. And Marshalls. And also, we can obtain a hierarchy of codes by adding constraints on this bipartite operation. And for example, since we hope to obtain some more tractable optimization problems, so one good constraint is the so-called PPT constraint. Eric Rains first used it to study distillation problem, and Liang and Marshalls use it to study quantum communication problem. And now the problem is just optimize all the possible code pi, which satisfy non-signaling constraint or non-signaling and PPT constraint to make this optimal success probability as large as possible. And our result is that the first result is that when assisted by non-signaling and PPT codes, the optimal success probability is given by this semi-definite program. And here, given channel n, Jn is just the Troy matrix of this channel, and M is the messenger size. And we maximize the trace of Jn and the operator F over these constraints. And when we need for the non-signaling assisted case, one just need to remove this PPT constraint to obtain this optimal success probability. So I'll give a sketch of how to prove this theorem. So as you can see, our target is to simplify or refine this optimization problem. So we first try to refine the objective function. The key here is to use the Troy matrix of the channel. And we suppose the Troy matrix of M is given by here. And we also suppose the matrix V given by the sum of projection KK. And the key here is this objective function is just given by the trace of the Troy matrix of M and the matrix V. This is some kind of classical analog of the channel fidelity of quantum communication, since this Troy matrix V, this matrix V is just the Troy matrix of the classical noiseless channel. And then, this will help us simplify the objective function. We further need to represent the Troy matrix of M by the Troy matrix of N and the Troy matrix of the code. This is based on, thanks to the results about transforming quantum operations by Tribella et al. And first shown by Liang and Marshalls. Then combining equation, these things, we can transform the objective function by this linear function. And then what we need to do is further impose the non-signaling and PPT constraint. And here we know that this non-signaling and PPT constraint are both semi-definite constraints of the Troy matrix of the bipartite operation pi. And then you will obtain a semi-definite program. And the final step is note that this matrix V has permutation invariance. So we can use this symmetry to further simplify the semi-definite program and obtain the SDP in our results. And then, since this is a general result for arbitrary channel, we use it to show some examples. For example, access the performance of amplitude damping channel. Let us take this example. We use this channel 3 times, and we hope to transmit 1 bit of classical information. We can exercise the optimal success probability here. And you can see when the parameter gamma is smaller than 0.4, it is possible to transmit 1 bit perfectly. And when the parameter is larger than 0.8, the error probability will go very large. Then we use it to consider the trade-off. That is the one-shot epsilon error capacities. The maximum rate such that the error is smaller than epsilon. We show that when assisted by non-signaling and PPT codes or non-signaling codes, the one-shot epsilon error capacity is also given by semi-definite program. Similarly, we also use Jn to represent the Troy matrix of N, and the whole quantity is can be efficiently calculated by SDP. And also, you only need to remove the PPT constraint to obtain the non-signaling case. And this quantity can also be used to study zero-error information theory. For example, we just need to set the epsilon equals to 0. This non-signaling capacity can recover the one-shot non-signaling assisted zero-error capacity in Duan and Winter's paper. And also, you can do the same thing of an SPPT case, and perhaps it will help us to lead new results in zero-error information theory. And since this, when we add assistance, it also provides Converse for the unassisted case. We compare our one-shot epsilon error capacity with other known Converse bounds. Let me briefly introduce them. The Converse for classical channel is given by Polanski, Pearl, and Verdu via the approach of the meta-converse approach. And then Wang and Reiner generalized it to CQ channel. And later, Marshall and Wiener further generalized to the quantum channels and give two SDP converse bonds. And in this optimization problem of hypothesis testing relative entropy, the first one is for the entanglement codes, and the second one is for the unassisted codes. And here, DH is the hypothesis testing relative entropy. And these two quantities can be transformed to SDP. And also, data and share also give converse for the entanglement codes, but it is hard to compute. And here, we show that the one-shot non-signaling and non-signaling PPT epsilon error capacity can provide better, efficiently computable converse bounds. That is, it is always smaller than or equal to the hypothesis testing relative entropy bound, and the inequality can be strict for some channels, such as amplitude damping channel. So then, we have already obtained the things we hope to obtain in the one-shot case. Then we use them to study the asymptotic communication capability. So I will briefly introduce the concept of strong converse. The converse part of the HSW theorem just established a weak converse, which states there cannot be an error-free communication when the rate exceeds the capacity. So as you can see here, if you communicate over the capacity, there will be some error. And the strong converse bound is something forbidden the trade-off. That is, when you communicate over the rate, as a rate over this bound, the error probability will go to 1 in the large limit n limit. And so we hope to push in this strong converse bound to a capacity, and if the capacity of a channel is also a strong converse bound, then we say the strong converse property holds. But unfortunately, the strong converse property for general channels is still open. So our key result here is a SDP strong converse bound for classical capacity. And we note the previously only known strong converse bound is the entanglement assisted capacity. And here, for any quantum channel n, the classical capacity is smaller than or equal to the C beta given by the semi-definite program. And if the rate over this SDP, the error probability will go to 0 when the channel uses increase. And there are several properties of this strong converse bound. The first is we can easily obtain some easy to computable upper bound. For example, here, just based on the trade matrix of the channel. And use this relaxed bound, we can easily show for any noiseless channel, this bound is tight. which means we can show the strong converse property for noiseless channel. And also, this SDP strong converse bound is also additive for different channels. So we show the brief idea here. The idea is consider n uses of the channel. We hope to use single letter formulas to estimate the success probability. So we hope to find some sub-additive upper bounds such that the n can be put outside of the formula. And here we provide the PS plus given by the semi-definite program. It is sub-additive and larger than the original success probability. Since it is sub-additive, we can use PS plus to the n to upper bounds the success probability of n uses of the channel. And then we can further show if the rate over this SDP strong converse bound, the PS plus is always strictly smaller than 1. Then consider n uses of a channel. Since we can put n outside of this PS plus, this quantity will go to 0 when n increase. And then we use this new bound to study some interesting channels. For example, for the amplitude damping channel. Applying this bound, we can show that the classical capacity is strictly smaller than this simple function of the perimeter of the amplitude damping channel. And we compare it to the previously best known upper bound given by Brando, Isot, Hordetsky, and Yang. As you can see in this graph, the blue dashed line is the previously best known upper bound, and our upper bound is this red solid line. And we give an improvement of this upper bound for classical capacity. However, we also draw the lower bound, known lower bound for the amplitude damping channel. And clearly, there is still much room between the upper bound and the lower bound. So the question is how to further improve the lower bound or the upper bound. And we also note for this case, the entanglement assisted capacity is originally larger than 1 bit, which means it perhaps given here. And this means our strong converse upper bound can be strictly smaller than the entanglement assisted capacity. The next example application is the strong converse property for new channels. The strong converse property has already established for several classes of known channels. The CQ channel, the particular covariant channel, the entanglement breaking channel, Hadamard channel, and some and the optical quantum channels. And here we introduce a new class of channels. This is kind of Q-tree channel with 2 cross operators, and we show that the strong converse upper bound is just equals to the capacity, which immediately established the strong converse property. This channel is actually quite interesting since in this case, its entanglement assisted capacity is 2 bit. And it's also strictly smaller than the quantum Lavoisier number. And this also solved another open problem in zero-error information theory. That is, the entanglement-assisted zero-error capacity can be strictly smaller than the quantum Lavoisier number. And also, for this channel, we can show the private capacity is also 1 bit. That is, in this case, the strong converse property also holds for the private capacity. And at the same time, the quantum capacity is strictly smaller than 1. So with similar idea, we hope to study the quantum capacity. The quantum capacity is given by the regularization of this coherent information. And as you can see, this quantum capacity is also difficult to evaluate. And there are 3 known strong converse upper bounds. The partial transposition bound given by Holevo and Wiener, and later proved to be a strong converse by Müller-Herms, Rieb, and Wolf. And there are also rings information given by Tomamicho, Wildy, and Winter, and also channels entanglement cost given by Berta et al. In 2013. So here, with similar idea, we derive a SDP strong converse bound for the quantum capacity. It is given by this kind of optimization problem. And if the rate exceeds this SDP Q gamma, the fidelity will go to 0 when n increase. And this result is built on the optimal fidelity of transmitting quantum information assisted by PPT codes, which is given by Liang and Marshalls last year. And the proof is just quite similar to the SDP strong converse bound for classical capacity we just showed. Also, this bound is tight for the noiseless channel, and we can show that this bound is additive on the tensor product. So we further compare our bound with the known strong converse bound. For example, for the partial transposition bound, here we used another alternative expression of complete bounded trace norm from Walsh's paper. And we can show for any quantum channel, the SDP strong converse bound is always smaller than or equal to the partial transposition bound. This can be proved by using SDP techniques. For example, we can construct feasible solutions of this complete bounded trace norm from the SDP of this Q gamma. And the inequality can be strict. We show example here. The channel is given by this cross operator representation, and we can show the solid line is the SDP strong converse bound, and the blue dashed line is the partial transposition bound. So, in summary, we first show the non-asymptotic classical communication assisted by non-signaling and non-signaling PPT-preserving codes. We show that when assisted by this kind of codes, both optimal success probability and the one-shot epsilon error capacity can be given by SDPs. And with this means we can totally estimate the trade-off under this assistance. And then we can use it to explore the limits of asymptotic classical or quantum communication. We can provide SDP strong converse bound for classical capacity and use it to provide improved upper bounds for amplitude damping channel, and also show strong converse property for new class of channels. And then we use similar idea to establish the SDP strong converse bound for quantum capacity, which improved the partial transposition bound. And however, there are still many problems unsolved. For example, we hope to find a tighter strong converse bound without using the additivity technique of semidefinite programming. And also, for this kind of basic channels, the amplitude damping channel, the classical capacity is still unsolved, and there is still a gap between the lower bound and the upper bound. And also, since we use this kind of NS and PPT codes, we hope to study how to implement this kind of code. And also, we do not know the relationship between the SDP bound and the rings information by Tomamicio, Wildy, and Winter. And finally, we hope to generalize this approach to study the continuous variable quantum channels. The details are given in these two archive papers, and I would like to thank my collaborators, Wei and Ren Yao. And that's all. Thank you.
Okay, so we have time for a couple of questions. Maybe Felix first, and then Mark second.
So in your SDP bound on the quantum capacity, if you assume that the channel is degradable, does that simplify somehow and give you something better?
Yeah, may I listen just the question again?
So in your SDP strong Converse bound on a quantum capacity, if you assume that the channel is degradable, does that simplify somehow and give you something better? I mean, do you get closer to the Korean information, for example, or?
Yeah, that's a good question, and I haven't dealt with this example, this case, and I guess perhaps. Thank you.
Maybe,
Just to clarify.
Yeah, good.
Your Q gamma, is that an upper bound on the two-way assisted quantum capacity, the quantum capacity assisted by two-way classical
I haven't
communication?
proved it is the two-way, it's just a one-way assisted.
It's just an upper bound on one-way assisted?
Yeah, just
okay.
upper bound one-way assisted.
So the first question related to what Felix was asking. In fact, I was about to ask how's your bound compared to the bound that we saw last year by David and his collaborator using approximate degradable channels? Because their bound is actually very tight, and it also applies to both classical quantum and private channels, like private capacities. So there's no comparison that I'm seeing in this talk.
Rephrase for you. So Debbie asked, have you ever compared your bound, quantum bound, with David's bound? David, last QRP, he
Oh,
has,
sure. Yeah, I compare. And I compare it in the full paper. So it's also the same channel. Yeah, just for this channel. And since I can compare this PPT bound, this SDP bound to the upper bounds gave by Suter et al. Via the approach of approximate degradable channels, and I can show when the R is larger than, for example, 0.2, this SDP bound is strictly better than the Suter's bound. Yeah, I calculated, and for this channel, it can be strictly better.
Okay. What about the amplitude damping channel?
Yeah.
Did you do the same calculation for the amplitude damping channel? Where your upper and lower bounds are very far apart, and I wonder where the earlier bound sits.
Also for the quantum capacity of amplitude damping channel?
The classical capacity for the amplitude damping channel, you show a plot where the lower bound and the upper bound are very far apart.
Oh, give me a minute.
Yeah.
Yeah, this picture. Okay. So this is the lower bound. This one, and the blue one is the upper bound, previously best upper bound, and the red line is the new upper bound given by SDP strong converse bound, and it improves, but still much room between here.
But so the question is, you said that the previous best upper bound.
Yeah.
So you already checked that it is worse than. So you already checked that this blue dotted upper bound is better than the one derived from the approximate degradable channel from last year? That works for classical capacity too, right? It works for all three capacities.
Any other questions? Okay, if not, let's thank the speaker again, and he would have a souvenir.
Yeah, thank you.